Okay, well, I'm really happy to be here. I appreciate the invitation. Uh, and I'm sorry I'm not there in person. There was, I think, fate did not have it in the cards to allow me to come. I did make an effort. Uh, I'm going to be talking about a rather new concept it's new to me too. I only started this a few months ago. I was actually preparing another talk for this conference when I came across this, and I worked kind of hard. I thought, well, this ought to work well. So we'll see how it goes. But keep in mind that it's a rather fresh concept for me as well as for you. I'm going to be talking about spherical blossoms. I'll define blossoms in a second. But the important thing is that it's a spherical analog for polynomial curves. And I have I'm going to breeze through some of this initial stuff because I think I've used up quite a bit of your time technically. But I was going to talk about the compass and the straight edge as being the two fundamental rigid body movements that we have. And when we think, for instance, of an airplane, we can talk about incrementing this with the straight edge, but we also need to use the compass to get its attitude as indicated by the airplane's attitude indicator. So two fundamental motions in geometry. The straight line has been well researched, but we don't get a lot of information about attitude. An attitude can be captured by points on a sphere. Basically we're just looking at the direction and we want to interpolate or use the points on a sphere for that. I'm going to skip through this quickly. I was going to talk a little bit, because I'm a history buff, about Boolean algebra. It's isomorphic to polynomial computation. It wasn't really proven until 1936. Polynomials approximate any continuous function. So really, we get a long ways with Boolean algebra, is what I'm saying. Polynomials are iterations of linear interpolation. This has been in math since, I think, Pascal, Babbage used it. Just this idea of iterating linear interpolation. It's going to be fundamental to what I say. De Costa-Joe algorithm is a good example of that. It works by taking, say I have a cubic control polygon here. It takes each leg of the polygon, and at a given parameter, it does a linear interpolation to get the new points. And then it takes the segments between those new points and iterates again until you get down to a point on the curve. Iterated linear interpolation. It's also, you see this triangle that's very closely related to Pascal's triangle. De Boer works the same. Different computation for the parameter, but iterated linear interpolation. All polynomials are iterated linear interpolation. That's one of my points. Now, Ramshaw back in 85, 86 came up with this concept called the blossom of a polynomial. This is going to be key. I'm going to try and reproduce this on the sphere. The blossom tells us a great deal about the polynomial. I hope to show you that. So if you haven't seen it before, look at this page. For every polynomial, degree d, there's a multi-affine function, the blossom of p, with d variables, such that I can permute the variables and I get the same blossom. So it has a symmetry about the permutation of it. If all of the variables are the same, I get the polynomial back. That's the diagonal property. And finally, there's this linear property. If a variable is broken up into a linear combination, alpha u plus beta v, I can pull the alpha and the beta out and add those together. Typical linear, except that this is a little stronger, where alpha plus beta has to equal 1, and that's the affine property, which is a special property of linearity. Take a look at this polynomial, or this blossom below. It's a function of u, v, and w. If you look at it, you will see that it doesn't matter what order I put u and v, w in. it permutes. If u equals v equals w, if I have all u's there, I get my polynomial back. You can even see how I might generate a blossom if you look at this carefully. And it's clearly linear in each variable, u or v or w. So this is a blossom. The interesting thing is we seldom use the actual blossom in the work we're doing. So it exists. Ramshaw proved it exists. It's kind of fun to look at. But what we're really more interested in are these three properties. I'm going to try and illustrate that for you. If I have 3 points, the blossom at 0, 0 is given, at 0, 1, and at 1, 1. So some point in space is given at these values. And I'm going to abbreviate just with the parameters. So blossom P of 0, 0 is just 0, 0. So I have these 3 points given. And if I use the affine property here, 1 minus u times one of those plus u times the other, u plus 1 minus u adds up to 1, I can find this point 1u on my blossom. And then where u and 1 minus u represent my constants, alpha and beta. I do the same thing on the other leg, exactly the same thing, and I get the point 0u. And then if I take this line segment between them, do it one more time, I get the point uu. Now we know from the blossom properties, uu must be on the polynomial. All I've done is use those 3 properties iteratively to find uu. If you're astute, if you've seen de Castelnau at all, you will know that I have just reproduced the de Castelnau algorithm. And that tells me that those points that I chose for 0, 0, 0, 1, and 1, 1 are Bezier points, whatever points they were. Anytime I write my blossom as 0, 0, 0, 1, and 1, 1, they will be the Bezier points that you see there. So very simply, we have done the de Castelnau algorithm, we've proven the Bezier, we can even subdivide with this. The algorithm comes from the blossoming principles. I can do something similar with de Boer. I'm not going to go into it in any detail, but if I have a shifted sequence, let's say minus 1 to 0, 0, 1, whoops, sorry, and then 1, 2, that algorithm will give me the de Boer algorithm. And there are lots of ways that we can characterize the different algorithms by how we designate the control points. De Castelnau is string art. So if I start here along this and I go from 1 to 1, 2 to 2, I do stuff that my mother did to make a kind of a tacky light fixture she put in our home. But you know, it was de Castelnau way back when I was in high school. Interestingly, if I pull that apart in 3 dimensions, so that you're viewing what look like in 2 dimensions as 3 dimensions, that blue thing that you see there, that is actually the blossom for that function. This is the parabola, the envelope here, and that's the blossom. My daughter Annika, after I explained this to her, set about making a widget for me, which I think is quite nice. Can you see me? Let's go back to this. I don't know if you can see me, but here's the widget. And if you look at it, it's the string art. And I have here, I always ask my students this, what's the equation of that curve? And they fuss about it. Very few come up with it until I say, well, figure out linear interpolation. The blossom, if I pull that apart, it's just that multi-affine. It's a bilinear function of u and v. You know, the interesting thing is, it doesn't matter how far I pull it apart. The envelope down here, that parabola stays the same. So it's invariant with the amount of offset I put in that blossom. Okay, that's de Castelnau in a nutshell. Okay. Now, to jump to the spherical analog, we first look at slurp. Slurp was introduced by Shoemake in 85 at SIGGRAPH. LURP is what we call a linear interpolation from A to B, as we've been talking about. Slurp then is a corruption of that term, where we use the great circle, we use an arc, which is part of a circle, and we interpolate along that circle. Call it a slurp, Schumacher's thing. It really is, when you define it, a quaternion. It's a great circle arc on the sphere. And here is the formula for actually computing that. I'm not going to use that much. So the people that engage know geometric algebra. You know the question to ask, is there an analog to the blossom for slurps, for these quaternions? And the answer is yes, in the infinitive. If I have two bivectors A and B, the bivector S, as the product of those, I can create a versor. I can basically rotate the vector V about using the normal, the pseudoscalar times S. I can rotate that. But this is a versor. It may not rotate it so that the length stays 1. Quite often, most often, we want that to stay 1. So we define a rotor where these vectors A and B are unit length. And then I get a unit rotation. So you know this, I think. That rotor can be written as a cis function, cosine theta minus b sine theta, where b is the bivector plane of A and B. Can be written then as e to the minus b2 for bivector b. And of course that leads us to the exponential form. Therefore we have the rotor operation, the familiar sandwich form that you see here of the exponentials. That's, if we stick to 3 dimensions, that's just the slurp. That's the quaternion case. But of course, the nice thing about geometric algebra is that we're not confined to 3 dimensions, and it is a coordinate-free case. So there's a lot of things there. Versors, we know, can actually decompose into a rotation and a linear function of the angle. Hestenes talks about this in his book. This connects slurps with more general geometric algebra. The second case is more interesting to me. Versors decompose into a linear function, and this suggests an approach to blossoming on the sphere. So consider the following versor. You'll see here that this is in 3D. If I restrict it to 3D, this is the geometric algebra of slurps. This is our versor. It's actually our rotor. This is the unitary part, and this is the scaling part that we have. So our versor divides into the scale and the rotation, as Hestenes said it would. What's important to note is this second versor is rotating me from a point on the first versor to a point on the other versor. So kind of like control legs, instead of linear interpolations, I have slurps. The important thing is the scale factor. Why? If I look at the norm of that versor, so that I have the norm of the scale factors times the norm of the slurp part, the rotor part, we know that the rotor part is unitary, so it disappears, and all we're left with in the norm is this function, 1 plus some offset times the angle phi plus some offset times the angle theta. That is a linear function. That's a bilinear function. That is our blossom. And it looks like, so the control frame for it is this, but it simply measures the distance from the sphere up to this blossom, what I call the blossom. So it's just a linear distance of angle to the sphere based on the angle theta. The actual intersection of this blossom with the sphere, where that is where the norm is equal to 1, is the curve on the unit sphere that I have dotted here. So this is what we define as our splossom. Once again, I'll repeat myself because it's important. The same way that a blossom measures distance to the planar domain, the splossom measures distance to the spherical domain. That's the key of thinking about it. And the diagonal, thinking again of our thing here, the diagonal is that cut through the center. The diagonal, in the case of the splossom, is the intersection with the sphere. And that's our designable curve. Here are a couple of views of the splossom where I'm just looking at the theta parameterization, incrementing theta and then drawing the phis. It's kind of an interesting looking character. Interestingly, it's quite easy to show. Each of those fibers of the splossom is an Archimedean spiral. That is radius times constant times the angle. So our little segment here of the Archimedean spiral. That's nice because we know a lot about the Archimedean spiral, like arc length and curvature. So immediately we have insight to the splossom. Here's an important thing I picked up from Ramshaw's second paper, Blossoms or Polar Forms. He suggests down here, oh, dang. Oh, where did I go? The part in red. He says, listen, it's better to turn things around and define a polynomial to be the diagonal of an affine function. And so I'm taking that quite literally and saying our polynomial on the sphere is going to be the diagonal of our splossom. I'm not going to try and define it as some kind of polynomial as we know it and then map it to the sphere yet, but think of it as the n-affine function, the splossom, the diagonal of the splossom. I'm going to call it a spolynomial. It takes a certain amount of hubris, I think, to rename splossoms and spolynomials. So I'm open to anybody who wants to challenge that, but I think it'll work for the talk. It gives me something to reference. Okay, so the splossom, the spolynomial readily generalize in the geometric algebra. So all I have to do is keep sandwiching more of these together and keep adding more offsets in here. And I come up with a form that is for any degree. In fact, one of the consequences of this is if I have a couple of control frames on the sphere and they share the same quaternion, the two arcs here are on the same great circle, and they have the same point where they start and end, just like Bezier, then I can guarantee you have tangent continuity there. G1 continuity, we call that. However, what's notable about orientations is that the G1 continuity is not enough. If we talk about, designing in CAD/CAM, G1 continuity is often all I care about. It's the manifold and not the parameterization that matters. However, in orientation applications, it's notable and significant that C1 continuity is important. The parameterization is important. Imagine, if you will, one of the reasons people get sick in VR is because of how rapidly the animation path is changing from left to right. Imagine if the continuity, that C1 continuity is, the change of view angle is discontinuous. Even worse, in robotics or CNC machining, it's impossible to have a discontinuous angle of speed. Right? You can't infinitely accelerate that guy. So one of the problems with slurps and the stuff that Schumacher did back there was it didn't give us a good way to get C1 continuity, which was important for orientations. But notice this. If I take for my offsets, instead of taking equal and opposite, I take different offsets, one for the outside, one for the inside. I get a different parameterization, but I get the same manifold. This polynomial here is the same curve on the sphere, but the parameterization is different. As you see, red is one of them that goes from the outer Red's polynomial to the inner Red's polynomial, and green is the other one. I don't know why I mixed up green and blue, but green should be blue here, and you get a different parameterization. We should be able to use this to match continuity at the endpoints. Even more, they don't even have to be opposite and equal. They do have to be negative and positive, but here's a case where they are really just altogether different in these two cases here. And we get yet another parameterization, but we get the same manifold on the sphere. Okay, that leads me to the final word that I want to put here. So I told you this is very young. It's very much an embryo. And a lot of the stuff I'm presenting here doesn't have a rigorous proof yet. That's a burden that's still ahead of me. But I'm pretty sure of what I'm presenting. It programs up well, and I have a good geometric idea in my mind of why it works. So I've yet to do the formal proofs. And I hope you maybe will take that as a challenge. I'd be happy to let somebody else do the proof. But you know how it goes. Lie algebra to Lie group. So, you know, if you're just looking at the sphere as a Lie group, and you look at its tangent plane, its Lie algebraic is described on a Lie group, depending on the group operations. Well, our group operations are on the Lie algebra are just these linear interpolants, right? And they, by use of the exponential map of Lie algebra, they map basically to geodesics, which are our versors, well, are our rotors on the sphere. So there's a very tight relationship between what we've been doing and the rotors, between the linear interpolants in the tangent plane and the rotors on the sphere. So we can then map using that exponential Lie group exponential map from the control polygon to the spherical polygon, I guess we can call it spolygon. We map from lerps to slurps, we map from polynomial to spolynomial, and from blossom to splossom, using the exponential map. Interestingly, the exponential map I'm talking about is Lie algebra to Lie group, but when we go back to our versor, we see the exponential map was something we derived through the geometric algebra as well. So, you know, that's my thinking on this topic. It's a project. It's a working project. I have a lot of questions on continuity, the proofs. There's a lot to say there. All this stuff can be applied to the different applications that I noted. In the conformal geometric algebra, and this is actually where I started thinking about it, you can do splines, you know, because in the conformal geometric algebra, a sphere represents a point back in Euclidean space. So you can do splines of spheres, hyperspheres, and hyperplanes. Lazenby and Hugo, I can't remember. They worked on this. There's several, I know that so has Hildenbrandt and a few others. Something I want to get back to, many interpolation forms I want to do on the sphere. I want to do the analogs of NURBS and Lagrange and Hermite and all those on the sphere. And I want to explore this Lie algebra Lie group connection, the exponential map. So thank you. I don't know the way things were kind of messed up, how I'm doing time-wise. Either we have a lot of time or we don't for questions. But I appreciate your attention. Okay, I should probably stop sharing. I might, yeah.
If you have a question,
Yeah, I'd really appreciate it if you can type out your questions. Oh, great, 10 minutes. If you can type out your questions, because I'm having some trouble, some echoes hearing you. Besides, my hearing is bad. You know, things happen when you get old. Thank goodness I'm still doing math. Okay, thank you. So, any questions? What are the applications in other fields? Well, that's a good question. I did attempt to show you some photos. So I think the ones that come immediately to me because of my background are the when you're watching a movie and the camera does a fly through a CG, somebody has programmed that path through those computer graphics models. And that path contains both position and orientation, because the direction that camera points is very important in that path. If that path swings too fast, its covariant acceleration is too fast, you're going to get disoriented. And if it happens too often, many people get sick. That's motion sickness. That's one of the causes. So animation paths, we see it in movies, we see it in sci-fi, we see it in scientific visualization. The other one that comes immediately to mind is computer vision. So in computer vision, I have a lot of pictures of unknown cameras of an object, and I want to reconstruct it. Oh, yeah, anyway, so reconstruction, computer vision, photogrammetry, where I take pictures and I want to reconstruct the object. There's many of those. So the next question that comes up is geodesic on a sphere. How about a hyperboloid? Yeah, how about an ellipsoid? All of this is great. Something I want to do is, all we really have to do is come up, in a series of papers that the Hestides and Hongbo Li and myself did. We did conformal algebra for hyperbolic and elliptic spaces as well. Think about getting a multilinear function that measures distance to these surfaces, and you can reproduce this idea. I think it's an excellent question. It'd be great if somebody wants to do that. GB, you should do that. No, it's not just a coincidence. The special case of the sphere has so many applications, and that's where Shoemake and all the others came from, is that the sphere gives us our orientation in space for all those orientation problems. But yeah, absolutely, Peng, the other spaces are all very interesting. We want to find the analog to BLOSSOM in hyperbolic and parabolic and elliptic spaces as well. I'd love it if somebody wanted to pick that up. I'm going to be busy with the other things. You know, the nice thing about hyperbolic space is that their geodesics tessellate the space. I mean, you can have any number of tilings, right? And that would be interesting to explore using this idea. Another interesting question, spline in space conversion to splosum. Yes, I mean, basically, there's a categorical analog here where if I'm doing a spline, let's say B-spline or any other spline, and I'm using the de Boer algorithm to evaluate it or whatever else, I can just lift that to the splosum. I mean, I do the spline, I come up with the spline algorithm using the blossom of the spline, and I can lift that to the splosum, and I get that. This is one of the directions I want to go. I want to do a B-spline. I really don't know what to call it, a B-spline on the sphere using splosums. Does that answer your question? Okay, looking at this. Say I have an arbitrary Bezier spline in 3D space. I would give an infinite list of points. How would you find, well, if you have a Bezier spline, each segment's going to have some degree, right? So it's not infinite. You'll have D number of control points. That means the splosum will have D arguments. It'll be a multi-affine function of D arguments. And you just use that, you can use those rules again. It's just like with Bezier, if you're using the blossom in Bezier, higher degree just means you have more iterations. Exactly the same on the sphere with this blossom, just more iterations. But each iteration is the same. It's a geodesic iteration. If you type it, I don't know if you're talking to me or not. Wish I could be there to see you guys, really do. Okay. Oh, now that's a good question. Do I need to do I think what's lovely about this question is the question is the same in spherical space as it is in Euclidean space. Do I need to do an approximation, or can I do, say, a least squares version of it? The least square is a polynomial. There's certainly a splosum there. There's a theorem by Ramshaw that, in fact, that says the if I have piecewise polynomials, the degree of continuity in the overlap in the blossom represents the number of multilinear fibers that coincide. So if I had, like two of these guys, and one of them matched along the entire edge, that would give me 1 degree of continuity. And if I had a higher dimensional version of this and I mapped along the plane, every time I raise the mapping where they coincide, I raise the continuity order. So it's more than just piecewise or fit a full curve. It's the order of continuity that we can talk about. It's a good place to explore. You should look that paper by Ramshaw, Blossoms Are Polar Forms. He talks a lot about continuity and how blossoms, they're overlapping, gives you a nice theorem there of how that determines the continuity.
So I think that's a good line on with the basis and that's a bit of pause.
Okay, thank you. Yeah, it's been great. I always figure if there's technical problems, it means it's something worthwhile. So I hope that's true. Anyway, good luck. Okay.
Gustav is there, and
Yeah. Get in touch with me if you want to talk more. My email's on the slides. I think on the first slide. Okay.
And you honestly on hospital, so you share oh, first we need to open it.
Do I have to turn it over?
Thanks. That's fine. That's fine.
Okay.